Maybe we could just ignore it altogether. Yeah. But if somebody asked you, what does a negative entropy mean? What would you tell them?
No disorder.
That there's no disorder.
No heat dissipating.
So if I have AL3 plus AQ, it's totally ordered. I mean, it's beyond ordered, because ordered, totally ordered would be 0. So this is going to be negative. It's got to be even more ordered than perfect order. Or, you know, why didn't they just call it 0 if it's perfectly ordered? Aluminum 3 plus must be highly ordered. You know, each aluminum must be evenly spaced apart. You know.
Imagine they'd be more disordered because of the charge.
Yeah, I mean, you would assume it'd be kind of disordered because it's AQ. AQ means there's translational motion. They can move anywhere it wants. Maybe it has to follow a certain path only in solution, each ion. No, there's got to be another explanation. And the other explanation to this is this. This is a weird table. Do you guys remember this table from Chem 1A? Right? What is unusual about this table?
Standard.
Well, standard conditions, well, that's not too unusual. Standard, what do standard conditions mean? It means that the gases are at 1 atm or 1 bar, and the concentrations of 1 molar. And anything else? It turns out that 298 Kelvin is not a standard. And the reason 298 Kelvin is not standard is because a lot of people don't want to do the reaction at one temperature. They want to do it at other temperatures. There's a lot of variability. Because at room temperature, sometimes reactions are just too slow. So they want to heat it up. And so it's hard to agree on a standard temperature. But most people will agree, okay, 1 molar or 1 atmosphere, that's okay. But that still doesn't, what's unusual about this table? Does anybody remember what's unusual about this table?
Is it because, like, depending on which side of product is on the reactant side, or?
It doesn't depend on the side.
The side
Yeah.
change.
The sign does change, yeah, for certain things, you know, but that's when we use the numbers, not necessarily with the table. There's something inherently weird about this table. What is it? So if I ask you, what has a higher entropy, aluminum or aluminum 3 plus, AQ? What would you say has a higher entropy? Aluminum solid or aluminum 3 plus? In other words, I'm asking what's more disordered. You would say aluminum 3 plus has a higher entropy? Yes? Okay. What has a higher entropy? Aluminum chloride solid or aluminum solid? Aluminum chloride? Okay, maybe you're okay then. I think that's, I think you got it then.
But what's the point of having a negative in front of aluminum ion?
Maybe, well, what if they change it to positive? Still be higher? Then where does the number come from? Where does that number come from? And so this is the strange thing about this table. The first strange thing about this table is this. If somebody were to ask you, what's a higher temperature? You know, what's a higher temperature? Minus 10 or 5? Minus 10 or 5? Well, I'm not telling you. Okay, what's higher temperature? -1 or 0? No, -1 is a higher temperature. Why? Because I'm asking you, -1 Celsius versus 0 Fahrenheit.
You didn't specify. That's you.
Yeah, you'd say that's a nasty question, right? So I would say, ha, you got it wrong. But then you would say it's totally unfair, right? Because I didn't tell you. Well, that's the problem with this table. Remember, the problem with this table is that this table is like, this is what I said in Chem 1A. This table is like having the Fahrenheit, Celsius, and Kelvin temperatures all mixed up, right? And so when I asked you this comparison, this was not a fair comparison because this was like Kelvin, this was like Celsius. So yeah, okay, yeah, 321.7 is actually higher than this because they are defined differently, right? And so why are the numbers defined differently in Appendix D like this, and why do they throw them all together? I don't know. You know, I talk about this in Chem 1A. I spend maybe 1 hour total out of the semester talking about this. Same thing in Chem 1B. So sometimes I think, gosh, I'd just rather have them make 3 separate tables. Why don't they just make 3 separate tables? One for Celsius, one for Fahrenheit, one for Kelvin.
In the description at the top, it describes the aqueous solutions as relative to values of 0.
Yes.
I have no idea.
Well, because they talk about this in chapter 7. This is, the first time you encountered this is here for hydrogen. You'll see an unusual entry for hydrogen. Yeah. For hydrogen, going back to chapter 7, if we want to form 1 mole of hydrogen gas, we're looking at delta H formation. We form it from 1 mole of hydrogen, the element, in standard state, hydrogen gas. And so when we look at the delta H, we form 1 mole of hydrogen from hydrogen. Is there any energy change? Well, there's no change, so there's no change in energy. Delta H has got to be 0 kilojoules per mole. Well, it's a mole, so it's 0 kilojoules. But if we were to form 1 mole of 1 molar H plus AQ from the element hydrogen gas in the standard state, we'll balance it 1/2. What's the energy? There's got to be some energy change here because we're going from H2 gas to H plus AQ, right? There's got to be some energy change here. But you look at this and it's 0. There's no energy change. Why is there no energy change? Is it just by coincidence it's 0? No, it's not by coincidence it's 0. There is an energy change. And so why didn't they just put the energy change number in there? You know, this has got to be, this has got to involve some energy. We got to break that bond. We got to knock off the electron. Knocking off the electron alone is like 2,300 kilojoules per mole. And then we're going to hydrate it in water. Well, hydrating is going to release energy. But why is there no energy change here? Does everything magically just cancel out? No, it doesn't. It's a reference point. It's called what we call an arbitrary 0. Somebody just said, okay, I'm going to define it as 0. So it's defined as 0 by somebody. Why? And so, well, in chapter 7, they tell you why. There's a paragraph about this, right? But does anybody remember? Why? Let me give you a hint. HCl. It's too hard, right? It's too hard because of this. If we look at the delta H formation of HCl, right here, it's minus 167.2. So this is in chapter 7. You can read about it. So 1/2 H2 plus 1/2 Cl2 gas. this is going to yield, well, 1 mole of HCl, 1 molar AQ. Here. It turns out that delta H of formation for HCl under standard conditions is minus 167.2 kilojoules. Well, HCl-AQ doesn't consist of molecules. HCl-AQ consists of H plus AQ plus Cl minus AQ. And so what I want to do is I want to zero down. I know to form both of these costs or releases this much energy. And so what percentage of that 167.2 is due to the formation of H plus, and what percentage of the 167.2 is due to the formation of chloride? So would you just guess 50-50? You know, half that energy was used for the H plus, the other half was for chloride. So 50-50 split. It seems fair, right? 50-50. Or maybe an 80-20? Or what do you think is a fair split? Well, you don't want to guess that, right? You want to know what it is. And so basically we have 2 unknowns. We got 2 unknowns. We want to know how much of the total was due to H plus, how much of the total was due to chloride. If we have 2 unknowns, what do we need? We need 2 equations. But there is no 2 equations. We only have 1 equation. We have 1 equation with 2 unknowns. If we have 1 equation with 2 unknowns, 90% of the people will say, forget it. You can't solve it. It's impossible to solve, right? But some people won't give up. And the people who won't give up will say, you know what? I'm still going to solve it. I'm going to assume something. What did they assume? They assumed it's a 0-100 split. And so they said, you know, I don't want to give up. Even though I have 2 unknowns and it's impossible. This is impossible to solve, right? 2 unknowns, 1 equation. There's no other equation. Well, actually, I shouldn't say it's impossible. Theoretically, you can do some, you know, we can't measure this. Can you do a calorimetry experiment and say this? I just want to form the H plus. I don't want to form the chloride. I'm going to do a calorimetry experiment and just form H plus. Will that work? You know, because we want to measure the heat, so do calorimetry. Can you form H plus alone? Why not? Yeah, it's going to be impossibly unstable because it's just going to be positive ion. You need to neutralize that positive charge with negative charge, otherwise. And so you cannot form cation with no anion. And so we've got to form both of these. Well, if we form both of these, then we're stuck. Well, so you can't separate this and do separate calorimetry experiments. Otherwise, we would be okay. But the other option is just to do this theoretically, you know, using computer. But you know, theoretical calculations are tough, and maybe not so accurate. And so, what do we do? Well, some people, they didn't give up, and they said, well, they're going to define x as 0, and therefore y is minus 167.2. Oh, that was easy. Now I'm done. I solved the problem. You know, I have 2 unknowns. Easy. Fixed, right? That's what they did. But you go, is that right? That can't be right. Well, it isn't. This is a huge error. No energy for the, that's a huge error. And so this huge error, well, you know what? This huge error is not a problem. The huge error is not a problem because all the H pluses are going to be a huge error one way, and all the Cl minuses will be a huge error the opposite way. And so when you add them up, those huge errors cancel each other out, and we got the right answer, right? And so when we add these 2 up, we get the right answer. It sounds ridiculous, but it turns out it's not. It's not ridiculous because whenever we form a cation, the cations are going to be referenced to H plus being 0. And therefore, any cation is, this is like the Celsius scale. And so any cation here, that's fine. We're always going to be off from the Kelvin scale. And then the anions are going to be referenced to chloride, right, being minus 167. And so all the anions will be off. So the anions will be like the Fahrenheit scale, the cations will be like the Celsius scale, and the elements and compounds will be like the Kelvin scale. So we have 3 different numbers with no, all the units are the same, but we have 3 different numbers wrapped up into the same table. And so it's your job to figure it out. And so this table is like the person trying to play a joke on you. The person trying to play a joke on you is going to ask you, what has a higher entropy? H plus AQ or H2? And you go, oh, it's got to be H2 because it's 130 versus 0. Well, it's actually true, but it does have a higher entropy, but you can't compare these 2 numbers. It's impossible to compare these 2 numbers because these are not on the same scale.
What if you convert?
Huh? Yeah, well, if you convert it, then you can. But how can you convert it? Because you don't know. And so we just leave it. And so what happens is, since you cannot form a cation without forming an anion, and the cations are all going to be offset one way, and all the anions are going to be offset the opposite way, when you add the cation with the anion, the 2 systematic errors cancel each other out for all these, and we're okay. And so that's why this works. Does that make sense? All right. Okay, so we see that again. This. So it turns out that the we can't compare these 2 numbers. So we just guess that solids are more ordered than liquid phases like AQ, and therefore this should be at a higher entropy. We look at those numbers, and so well, if that's the case, then if this is negative, then what's my 0 for entropy here? This is negative 321. What's the 0 point got to be?
This is still H plus.
Yeah, it's still H plus. And so it makes sense just to use the same 0 for everything. And so if we go to H, let's take a look at H plus AQ. H plus AQ has a delta H of formation of 0, which was arbitrarily defined. It also has an absolute entropy of 0. And this was also arbitrarily defined as well. This was defined as 0 because certainly H plus AQ is not a perfect crystal at 0 Kelvin. And so here, all the cations are referenced to this. Is there an anion 0? No, there isn't, because the anions can be offset. And so what they can do is they can measure the heat capacity of HCl, let's say AQ, and then determine entropies from that. Okay. So what you need to do is you need to take a look at the numbers here and then come up with some generalizations. And you can see some patterns. And rather than taking the time and looking for those, I'll just tell you. But me telling you, it's much better if you find these yourself. Most solids are going to range from what to what? Most solids range from 0 to about 100. Liquids are going to range from 100 to 200, and gases will range above 200. Right? There are going to be outliers. For example, there are going to be some solids that lie outside that range. So you're going to see some variation. So if you look, aluminum has a fairly low entropy, 28.33. But let's take a look. Aluminum chloride has a much higher entropy of 110. But take a look at aluminum sulfate. Aluminum sulfate has an unusually high entropy, 239. Aluminum sulfate is kind of an outlier because aluminum sulfate, you know, it's got to be the sulfates have a lot of different vibrations. Maybe the sulfates can actually rotate in the lattice, and so that introduces more entropy there. But solids are typically 0 to 100. Some solids are going to be unusually high. Some solids are going to be fairly low. Like, what do you think has a really well-ordered crystal? Think about it. What crystal can you think of that's pretty well-ordered at room temperature? Sodium chloride? Let's take a look. And so we go to sodium chloride, 7213. Is that really all that? No. There could be defects in there. Can you think of anything else that's really well ordered?
Diamond.
Diamond. Diamond should be really well ordered. Let's take a look at the entropy of diamond. Should be carbon. So if we go to diamond, diamond's entropy is 2.38. In fact, you know what the lowest entropy is on this table? 2.38. It's the lowest entropy on this table, diamond. And so, well, what about the highest entropy? You know, and so we could go through and take a look. And so this gives us ways to generalize. So first we take a look at the numbers and get an idea, but it turns out that entropy calculations are quite easy. So let's do an entropy calculation here for this reaction. We got 1/2 H2 gas plus 1/2 Cl2 gas. This is going to go to H plus A cubed plus Cl minus A cubed. The enthalpy calculation is really easy. Delta H is minus 167.2 kilojoules, but what is my delta S for this reaction? So let's go ahead and calculate delta S. Delta S is the S final minus S initial. And so we just look at the final entropes and compare it to the initials. So well, this one's easy. What's the entropy of H plus? 0. And the units are joules per mole Kelvin. And then I have 1 mole of that, and so it'll just be 1 times 0, which is 0. What about the entropy of H2? Is that 0 as well? No, the entropy, you know, the standard enthalpy of formation is 0, but the entropy certainly is not 0. In fact, it's a gas. So we guesstimate that the gas should have an entropy greater than 200. And so let's see what the entropy comes out to. What is it?
130.7.
130.7. So it has kind of a fairly low entropy. It's so here, 130.7. But we only have 1/2 mole, so it's going to be 1/2 mole times 130.7 joules per mole Kelvin. Chlorine, which should be comparable to hydrogen, so let's take a look at the entropy for chlorine. Here's chlorine gas. Oh, actually, it's quite a bit higher. 223.1. 223.1 joules per mole Kelvin. That's going to be 1/2 mole. This is, we have half as much gas as should have half as much entropy. And then the entropy for chloride, we can take a look here. Entropy of chloride is, actually, that's pretty low, 56.5. And so why is that so low? It could be that the water molecules orient themselves around the chloride. 56.5. We have 1 mole. that. And so we just look, we take the entropy final. The final entropy is just going to be 56.5 joules per Kelvin. The initial entropy is going to be 1/2, so this is going to be 65.35 joules per Kelvin, plus half of that, 223 would be 161.05. Is that right? One 1.55? Oh, okay, thanks. 111.55. Yeah, that's right, 223.1. 0.55 or 0.5? Oh, that's right, because of the point over. Yeah. Negative 120.4. And so when you look at this reaction, we're going from gas to liquid phase. And so gas to liquid phase, you'd expect, well, gases are about 200, liquids are about 100. So delta, the change in entropy should be about 100. And so that's what we see here. We got about a 100 joule per Kelvin drop in entropy. So the entropy is decreasing. That means we're going from less order to more order here.
So what does the negative number tell us?
The negative number tells us that entropy is decreasing. Entropy is decreasing, and in nature, we want entropy to be increasing. And so, what do these numbers tell us? Well, now we can compare. We have delta H. Delta H for this reaction is minus 167 kilojoules. Delta S of the reaction is minus 120.4. So here, energy is going down. Energy going down, that means we should have reaction. But entropy going down is not good. We want entropy to go up. We want to maximize entropy, so it says no reaction. So we have a conflict here. One of these says reaction, the other says no reaction. So what do we do in terms of a conflict? Well, we have to compare. We have to see which one dominates, because sometimes the energy term dominates, sometimes the entropy term dominates. So in this particular case, now we have numbers. How can we compare those numbers? Well, the units are different on the numbers. The unit here is kilojoules. The unit here is joules per Kelvin. And so what should we do? We can't compare the numbers directly because they don't have the same units, for one. And maybe it's not fair to compare entropy with energy. Maybe we can't do a direct comparison. But one thing we might try to do is, well, we know what the temperature is. What is the temperature? At 298 Kelvin, we can cancel out the Ks. And so multiply this number by 298 K, and we should get what? $35,800. So we'll just go 35.8 kilojoules, negative. All right, now let's compare. This is negative 167, this is negative. We want a negative here for delta H, but we want a positive here. And so now is it fair to compare? Well, maybe we can compare them. when you compare this, this looks to be more favorable than this is unfavorable, right? This is unfavorable by 35.8. This is favorable by 167. So it looks like 167 is bigger than 135.8, and so it looks like we're good. What do you think? Can we compare them like this? It turns out, yeah, there's reaction here. There's reaction. There's driving force for this. And so this doesn't seem right, but you know, if you call this anti-driving force and that driving force, then this driving force wins. Delta S should be positive. But that's not so easy to do. And we don't know, is that right to compare it directly? And so we're going to take a look at that in more detail next. But before we do that, I want to talk about one other thing with entropy. And that is this. You know, what's the difference between a rule and a law? What's the difference between a rule and a law? Yeah, a law is some kind of pattern in nature, you know, that's reproducible, repeating this pattern. A rule is what? A rule is too many exceptions, typically. And so there's something called Troughton's rule. I was thinking to just skip this entirely, but you know what Troughton's rule states? Troughton's rule states that the delta S of vaporization, so delta S of vaporization, we go from a liquid to a gas. If we go from a liquid to a gas, liquids are about 200, gases are about 3, liquids are about 100, gases are about 200. So delta S should be plus 100, right? Roughly. And so delta S of vaporization should be about plus 100 based on, you know, just a guesstimate. But what Troughton's rule says that delta S of vaporization for any liquid should be 87 joules per mole. 87 joules per mole, well, you know, how precise do you think that is? Do you think Troughton's rule has a lot of exceptions or very few exceptions? A lot of exceptions, right? Troughton's rule has a lot of exceptions because the number is going to vary. For example, one of the exceptions is water. You know, water has a much larger delta S because liquid water is much more ordered than other liquids. Liquid water is much more ordered because of the strong hydrogen bonding interactions, which locks the water molecules or constrains them and fixes them in certain positions. And so there are a lot of exceptions for Troughton's rule. Where Troughton's rule works best are for organic liquids. A lot of organic liquids will come close to 87, but you know, there's a pretty wide spread. And so this isn't the high precision number here. It's not like, oh, it's 87. You know, this is getting a little bit too precise. And so I wasn't going to really talk much about that here. Instead, I wanted to talk about this because here's one way we can compare the two driving forces and to see which of these two driving forces dominate. But, you know, is that right? Compare the numbers like this. You don't know. And so what we look for is, you know, maybe what do all spontaneous means there's a driving force present. Reactions have in common. All spontaneous reactions have in common the fact that delta S of the universe, the entropy change in the universe, is greater than 0. And so if we look at any reaction, you know, it doesn't matter if the energy goes up or down or the entropy goes up and down. All of them have to be accompanied by an increase in the entropy of the universe. And this is called the second law of thermodynamics. And so, do you know what the first law of thermodynamics is? First law was discussed in chapter 7. Yeah, that's it. That's the first law. The third law of thermodynamics? The entropy of a perfect crystal at 0 Kelvin is 0. And this is the second law of thermodynamics. The second law of thermodynamics says there's only one driving force in nature. The driving force in nature is that the entropy of the universe must increase. If the entropy of the universe decreases, then nothing should happen. You know, it's non-spontaneous. Mm-hmm.
So we said the highest entropy is 0, then?
The highest entropy?
Right? For the track is 0? Was it for the 2 by?
No, the lowest entropy is 0. The lowest entropy is 0, unless you're dealing with cations and anions, which have an arbitrary reference point. But even then, on an absolute scale, there's 0. And so the lowest absolute entropy is 0. You could have negative entropies, but those are on a arbitrarily defined 0-point scale. Does that make sense? Is that what the question, or was it something else?
No.
The highest entropy, you can go very high in entropy, you know, depending on the number of ways. But the problem is how, you know, do you think Appendix D is big enough to cover the entire universe? No, unfortunately not. And so we have to go back and we have to think about the universe in general. The universe we could subdivide into two subdivisions. What would those be? If we don't have to look at the entire universe. Let's break it up into 2 parts. We break it up into the system and surroundings. Okay. And so we'll look at the delta S of the system plus delta S of the surroundings. And then we just define the system. The system is going to be the reaction or process. And so we just did a delta S of system calculation. That was easy. It's delta S of the reaction, H2 plus Cl2 goes to HCl. We'll just use Appendix D. So this is easy. Use Appendix D. And therefore, delta S of the system is just equal to delta S of the reaction we're interested in or process. It doesn't have to be a reaction. A process would be like freezing or melting. This is hard, though, because the surroundings would be the rest of the universe. And so we have the same problem. This is going to be hard. It's hard because it's a lot of calculations. But there are thermodynamic relationships that we can take advantage of. And one of them is the thermodynamic relationship between delta S and Q. Entropy is related to heat. So changes in entropy are going to be related to the heat exchange. And so it turns out, let's get rid of that. Delta S is going to equal the amount of heat exchange between the system and surroundings and the temperature. This is going to be related to heat capacity, right?
Yeah.
This reversible, there are reversible processes and irreversible processes. In a reversible process, we do it infinitesimally slow, and everything's at equilibrium, so we can reverse it. But you don't have to worry about this too much. Turns out the amount of heat is going to vary depending on how you do it, but we know that because heat is not normally a state function. Heat is a path-dependent function. And so reversible, I'm not really gonna deal with it right now. If you continue on in thermo, then you'll talk more about this here. And so if we're interested in delta S of the surroundings, delta S of the surroundings is just equal to Q of the surrounding. I'm going to get rid of the reversible and just call it Q of the surroundings over T. And so if heat is absorbed or lost by the surroundings, where does it go? Oh, the surroundings is the universe. And so the surroundings is the rest of the universe. And so if heat is gained by the rest of the universe, it must have been lost by the system. That's the first law of thermodynamics. So, you know, there's another way of talking about the first law, and that is Q, the system. Any heat gained or lost by the system must have gone into the surroundings because energy is neither created nor destroyed. Right? Well, if we know that the heat was gained or lost by the surroundings, it must have come from the system. And so we just change the sign to indicate the direction of change here. And so delta S of the surroundings can be put in terms of the system here. Okay, so this equation is just given. This is what the entropy change is dependent on. And so this, we can substitute into our equation here. And so if we substitute delta S of the universe, which is way too much to deal with, is equal to delta S of the system, which is easy to deal with, plus this. It's going to be minus Q of the system over T. Well, the problem with heat is, you know, the amount of heat you're going to get changes depending on how you do it. I don't want the amount of heat to change. I always want the amount of heat to be the same. If I want the heat to be the same, I have to make the heat into a state function. And so in chapter 7, we made the heat into a state function. Which state function? Well, we made the heat into two different state functions, right? If we do the reaction under constant volume, we can make the heat equivalent to delta U. But if we do the reaction under constant pressure, we can make the heat equal. In fact, the definition, what is the definition of delta H? Delta H is defined as the heat, right, under constant pressure with P delta V work only. And so this will always give me the same amount of heat because I'm going to restrict the conditions I do the reaction under to constant pressure and P delta V work, and then we can substitute that here. And so this is going to be delta S of the system, you know, minus delta H of the system over T. So what we've done here is we've taken something that would have been impossible, that is the universe, and made that into something possible because delta S of the system is easy to calculate. What about delta H of the system? Is that easy? That's easy to calculate. Delta H of the reaction, in fact, we didn't even have to calculate it. For the last reaction we did, it was minus 167.2. All right, then we're going to multiply both sides by T. So we get T delta S of the universe is equal to delta S of the system, T delta S of the system, minus delta H of the system. Then we're going to multiply by -1, so we get minus T delta S of the universe. When we multiply by -1, that means this. We've got to flip our thinking. Because if the entropy goes up, that's good, right, of the universe. If the entropy of the universe goes up, then we're multiplying by negative sign, so this whole term is going to get more negative. And this is going to equal, I'm going to rearrange this, this is going to equal delta H of the system minus T delta S of the system. And then we're going to define this as a new state function. This is going to be defined as delta G. Delta G is G is called the Gibbs free energy. Gibbs free energy. And so what we end up with is this. we end up with delta G of our system, basically, is going to equal delta H of our system minus T delta S of our system. And we know this, if delta G is negative, then the entropy of the universe is positive, which is a driving force. And so what we're going to look for is what makes delta G negative. Well, if delta H is negative, that's good. So if energy goes down, that's good. But what about entropy? Well, we want entropy to go up because the more this goes up, the more negative this becomes. And so this energy goes down, entropy goes up, means our delta G goes down and the entropy of the universe goes up, and it's spontaneous. So anyway, delta G is negative. Let's do this. Well, what if delta H is negative, energy goes down, and the entropy goes down? Well, if the energy goes down, this is negative, but if the entropy goes down, then a negative times negative gives us a positive. So we got to see which one dominates. Which one's going to dominate is going to be like this. At we call this spontaneous at low temperature. Because at low temperatures, this term is going to be smaller, and it's positive. And so if this term's positive and smaller, then the whole thing can be negative. So this is going to be spontaneous at low temperature. But if the temperature is high, then the entropy term dominates, and it'll be non-spontaneous. So it's non-spontaneous at high temperature, spontaneous at low temperature. If the energy goes up, that's not good. But if the energy goes up and the entropy goes up, then maybe the entropy can dominate. The entropy term is good, so this would be spontaneous at high temperature. So the entropy term gets bigger and bigger as the temperature goes up. And it's going to be non-spontaneous at low temperature. If the energy goes down and the entropy if the energy goes up, if the energy goes up and the entropy goes down, that's unfavorable. Both of these say no reaction, no reaction, so this is non-spontaneous at all temperatures. So we'll just say non-spontaneous. This is spontaneous at all temperatures. And so these are the scenarios that we get. What we want is, sorry, I'm just going to erase that. What we want is this. Basically, if delta G is less than 0, that is, it's negative, then it's spontaneous, it's favorable. That means delta S of the universe must be going up. If delta G comes out to 0, then there's no driving force. We call this at equilibrium. However, if delta G is greater than 0, then that means it's non-spontaneous. And it turns out that the reverse reaction, this is a state function, reverse reaction will be spontaneous. So this is the way we're going to compare the two driving forces. There's actually just one driving force, the entropy of the universe, but we can break that into energy and entropy. When we break it into energy and entropy, let's go back to this problem. We have 1/2 H2 gas plus 1/2 Cl2 gas. This is going to go to HClAq. And we saw that delta H is minus 167.2 kilojoules. And delta S for this was, I forgot, but okay, joules per Kelvin. Well, we're just going to do it per mole of HCl. So.
I still don't understand why you multiply it in a negative one for the derivation for delta G. negative T delta S.
You don't have to multiply by -1. There's no reason to do that. You know, if we didn't multiply by -1, then it would be the opposite, right? And it being the opposite would have been better if they had defined delta G as T delta U, or excuse me, T delta U, T delta S of the universe. Sorry, it might have been easier because as delta G increases, the entropy of the universe increases. You know, I have no idea why they multiplied it by -1, but they did, and they defined it that way, and that's it. So we're stuck with it. So in other words, we want delta G less than 0. So let's do our delta G calculation here. Delta G of the reaction is going to equal delta H minus T delta S of the reaction, or our system. Our system is the reaction. So this is minus 167.2 kilojoules. I'm getting rid of the mole because we're forming 1 mole of HCl.
Negative 120.
Is it negative 120? Okay, minus T delta S. Well, the temperature, what is the temperature? 298 Kelvin. Delta S is this negative 120.4 joules per Kelvin. The joules don't cancel, but the kelvins cancel. But the joules and kilojoules, those units don't match. So I should convert it to kilojoules. Right? And so I'm going to convert this to kilojoules by dividing by 1,000. 1 kilojoule per 1,000 joules. And so this is what I get. I get minus 167.2 kilojoules versus plus, what was it, 35.8? It's 35.8 kilojoules. Which one wins? Which one's going to win out? Delta H. Delta H wins out because this is minus 167.2, and this is non-driving force. This is going to hurt our driving force, but not by enough. It's 35.8, won't cancel this completely out, and we end up with minus 131.3.4. What is it? 131.4 kilojoules. And so we say it's spontaneous. That is, there's driving force. And so essentially what we did before, the comparison worked, right? We're just seeing which one is the dominant energy. And it turns out that delta H is the dominant energy. The 35.8 wasn't enough to cancel that out.
It's actually 131.3.
131.3? Oh. All right. Okay, whatever. It's close enough for this. It's just rounding. It depends on how you round it, if you round it. If you didn't round it and you just kept it in your calculator, then it's different. So it's spontaneous. So this gives us a way. And so really there's one driving force. There's the second law, and that's the delta S of the universe. But we can break that delta S of the universe into an energy term and an entropy term. And so what we see is we want a negative energy and a positive entropy, right? In other words, we want to minimize energy and maximize entropy. And so then all our calculations, the calculations are quite simple then. To figure out if there's a driving force, then it's not just the energy, because the energy might go up and still we'll have driving force. And so now the calculations are going to be much easier because we can just determine it from this without much difficulty. And so what else are we doing in here? And so let me take care of one loose end in the S. one of the loose ends is, delta S is equal to Q over T. Well, what if the Q is a heat or phase transition? So this is the enthalpy of vaporization, or the enthalpy of fusion, or the enthalpy of one or the other. So we can calculate our delta S from this equation here. So the delta S of a phase transition is equal to the delta H of that phase transition at the temperature of that transition. And so what is the entropy change here of water? We're going from solid to liquid, which is delta H of fusion. And so to melt ice is going to take 6.02 kilojoules per mole. And so from this, we can calculate the delta S of fusion. Well, this just gives us an alternative, because we could already calculate delta S easily. We just get the entropy of the liquid minus the entropy of the solid. And so there are two ways to calculate it. As we're going to find out in thermo, there are a lot of different ways we can do the calculation. Okay, so let's do some more calculations here. All right, what are some more calculations here that we're going to do? This gives So we'll just verbally talk about this one. So here's a reaction we looked at. Remember this reaction, 2NOs plus NO2? We learned about the kinetics of this reaction. One mechanism that was consistent with this reaction is a two-step mechanism with the second step, right? But that's kinetics. We also want to know about the driving force. Is there a driving force for this reaction to occur? Kinetics is how fast that reaction goes, but thermodynamics, which is what we're talking about, is talking about, is there a driving force? And if so, what is the driving force? Well, this is a redox reaction. And so the driving force that we talked about in terms of redox is going from a stronger oxidizer, stronger reducer, to a weaker oxidizer, weaker reducer. So we could use that same thinking for this. However, there's another way we could do that. And the other way we could do that is by looking at the energy. So I look at the energy. This is favorable, right? Energy is going down. And then I look at the entropy. When I look at the entropy, is that entropy favorable or unfavorable? Unfavorable. And so in order to figure out if a reaction is going to occur here or not well, I'm going to have to calculate delta G, which is going to weigh the energy versus the entropy. And so in that weight, I see that the energy is minus 114, the entropy is plus 43. So the entropy was not enough to cancel out the energy, and therefore it's spontaneous. This reaction is spontaneous. However, what happens if I change the temperature? If I change the temperature, that's going to change the impact of the entropy. So if I do this at higher temperature, is it going to make this reaction more spontaneous or less spontaneous? Less. If I increase the temperature, it's going to make this less and less spontaneous. And in fact, if I continue to increase the temperature, eventually what's going to happen is that this term will cancel out this term. When that happens, delta G will be 0, and so it's an equilibrium. But if I keep increasing the temperature, then this term will be greater than this term, means it's going to go non-spontaneous. And so the next thing here that we're going to look at, because the standard delta G calculation is not difficult, I'm not going to do more examples of this. What we're going to look at is at what temperature will this go non-spontaneous. So right now at 298 Kelvin, if I look at this reaction, 2NO gas plus an O2 gas goes to 2NO2 gas, I see my delta G under standard conditions is equal to minus 70.4 kilojoules, which means it's spontaneous. And so the question is, at what temperature will it go non-spontaneous? And so I can change the driving force by changing the temperature. But there's one problem with that. And so what I want is, I want my delta G at this temperature. Which means I need my delta H at that temperature, and T's already going to be that temperature, but I also need my delta S at that temperature. Okay, let's go with delta S first. Do I know what the temperature is? No. And so how the heck am I going to figure out what the entropies are? Because the entropies change with temperature. And so do you see I have a problem? Well, this is the way I'm gonna fix that problem. The way I'm gonna fix that problem is the temperature's going up. And so what's gonna happen to the gas? Well, it's gonna become more disordered as the temperature goes up, right? But that goes across the board here. All of these are gases, so all of them are going to go up. So if the reactant gases go up in entropy, the product gases go up in entropy, the difference is going to be about the same. And so what we're going to say is this. We're going to say that delta H and delta S do not change much with temperature, as long as the phase doesn't change. Much with temperature. This is as long as the phase is solid, liquid, or gas, as long as the phase doesn't change. And so the entropy, you know, increasing temperature is going to increase the entropy, but it's going to increase the entropy of everything. So, you know, the deltas should be about the same. Therefore, delta H at any temperature is going to be about equal to delta H at 298 Kelvin. And delta S at any temperature will be about equal to delta S at 298 Kelvin. Of course, it'd be better if we knew the temperature and we knew what the entropies and enthalpies are. But we're just going to assume this is going to lead to a little error, but it's okay. Delta G, can we say the same thing? Delta G at some temperature is about equal to delta G at 298 Kelvin. Is this true? No, this is totally false, because I just told you here we can completely change delta G by altering the temperature. If we keep increasing the temperature, delta G is going to go to 0, and then it's going to go positive. And so delta G depends strongly on temperature. So this would be false. And so this is what we're going to do. We're going to solve for the temperature. The temperature is going to equal, what is that going to equal? So, well, if it goes non-spontaneous, you know, non-spontaneous means that right now it's negative. And so what I need to do is I need to get my delta G at some temperature to go 0. You know, when it goes 0, then I've canceled out the driving force here. And so I want that to equal 0. This is going to be equal to my delta H at that temperature minus T delta S at that temperature. And these are all going to be under standard conditions because there's no standard temperature, so I'll keep those under standard conditions. And so I'm going to solve this for T. And so what I get is my delta H naught is equal to T delta S naught at some temperature T. Solve that for T, I get T is equal to delta H naught over delta S naught at that temperature. And so figuring out that temperature, I just take my delta H, which is minus 141.1 kilojoules, divided by my delta S, which is minus 146.5 joules per Kelvin. And then I need to convert it, either joules to Kelvin or kilojoules, joules to kilojoules or vice versa. So we'll just convert it to kilojoules here. And then calculate the temperature. What does the temperature come out to? Well, 963. 0.13 Kelvin. All right, so if I plug that in here, then what I'm gonna get is, if I use that temperature here, I'll get minus 114.1 plus 114.1. They cancel each other out. And so the driving force is canceled out by the anti-driving force, if you wanna call it that. All right, we'll stop here and then we'll continue next time.